Thank you for your introduction, Ogawa-sensei. I'm Hiroki Saito from Tohoku University. First, I'd like to thank you for giving me the opportunity to talk here. Today's my topic is lightning damage protection of CFRP with cold sprayed metal coatings. This content is relatively new for our research group, so any discussion and comment would be happy for me. So let me start my presentation. The demand for aircraft is expected to be increased for long term, and energy conservation and reduction of environmental impact are important issues. So to address these issues, developing the lightweight aircraft is required using advanced lighter materials. For example, such as for engine, the titanium aluminide alloys is expected to be applied as an alternative to nickel-based superalloys, and or aircraft body, the carbon fiber reinforced composite, CFRP, this material is today's topic material, is already applied to aircraft body, which are previously made of aluminum alloys. In case of Boeing 787, the 50% of the component come from the CFRP. CFRP have a very good mechanical properties and also lightweight, but one of the weak point is the low electrical conductivity of CFRP. So lightning protection system is required to avoid the severe damage. As Saotome-san gave us a lecture in this morning, the airplane, the body and also main wing and tail wing, the lightning can strike all surfaces on the airplane. So the lightning protection system is necessary, differently necessary. And the conventional, so current lightning protection system is representative one is a copper, extended copper foil. The copper foil is a metal mesh like this, and the metal mesh is attached on the CFRP all surfaces. And when lightning impacts on the surface, this mesh acts as a current path, and your heating is suppressed, and severe damage should be avoided. But this metal mesh is treated by manually, and increased production cost and complicated repair process after lightning strike. This is a problem. So one attractive candidate, the attractive method is the cold spray method. The cold spray, I showed the schematic of cold spray process here. The particle size normally from 10 micron to 50 micron size particle put into the gas, and the particle particles are accelerated gas and impact on the substrate to get coating. This cold spray characteristics is first no phase transformation. No phase transformation means particle not melted. No experiences no melting, no phase transformation occurs. And simple equipment, so very simple equipment is also merit. And the first deposition rate, recently this cold spray system is featured as a additive manufacturing technique, and also ability to produce 6 deposits. So let me play the movie, a video of the actual cold spray process. This is a metal coating on metal plate. So the metal deposition. This is a copper particle on the aluminum alloy substrate. This is a normal metal on metal process. And this is a polymer coating on titanium bond coat. So the polymer coating on metal substrate. This is dissimilar material deposition. And also this is metal deposition on ceramic substrate. We can get the cone shape structure in short time. This cold spray system or cold spray technique is, I think, very suitable for metal formation on the CFRP. So this is an attractive candidate. But normally, when applied this method to CFRP coating, one problem is CFRP erosion by particle impact, because the cold spray normally particle impacts with high speed and particle experiences severe deformation. So it means it often causes damages on CFRP. So this is this figure shows particle impact cause erosion of the carbon fiber, and also the summary effect because cold spray. The name is cold, but actually not cold. Hot gas is exposed to surface about 300 temperature degrees. So the summary effect also causes CFRP erosion. So when applying this cold spray technique to CFRP coating, first we must consider is a cold spray coating without damaging CFRP, especially carbon fiber. So normally, relatively soft metallic materials such as tin, aluminum, and zinc, copper, the relatively soft material is suitable for deposition. And also, normally, cold spray is separated by two types, high pressure cold spray and low pressure cold spray. Low pressure cold spray is pressure is under 1 megapascal. This limited velocity is suitable for coating on CFRP. And after that, the second step, development highly conductive coating, for example, using copper or good conductive materials is important. So our group started research. The objective of this study is to develop a lightning protection technique for the high-speed formation of conductive coating on CFRP using the low-pressure cold spray as an alternative to conventional metal or mesh lamination. First, we try to develop a cold spray coating technique that does not damage carbon fibers. And after that, I will introduce the cold spray coating for protecting CFRP from lightning strikes. So let me talk about first, development of cold spray coating technique that does not damage carbon fibers. This slide shows the substrate and the cold spray parameters we used. In this presentation, I focus on the CFRTP, the carbon fiber reinforced thermoplastic substrate. And the cold spray parameter, during cold spray, we have to set many parameters like gas type, pressure, temperature, also traverse speed, and so on. We have to set many parameters, but impact velocity, the main parameters which affect the impact velocity is particle size and particle material, and also particle pressure and temperature. So in this experiment, we change the gas temperature from 260 to 340. We choose 3 different temperatures. We use the low pressure cold system, commercial low pressure cold system. The working gas is air and gas pressure is fixed at 0.5 megapascal. The standoff distance and traverse speed and other condition is like this. And because we want to estimate the particle momentum effect on erosion of CFRP, we use the 3 different size copper particles. So with the average size is 5 micron and 10 micron and 20 micrometers. So the particle size is doubled and also doubled. The particle shape is almost spherical. So let me move on to the result of coating on CFRTP. Now we can see the temperature effect in horizontal direction and size effect on vertical direction. First, we focus on the gas temperature effect. For example, when we see the 5 micron particle case, the deposition rate increases with increasing gas temperature. But at the case of 340 degrees, coating delamination was observed, and so overheating substrate resulted in coating delamination. The tendency is similar for 10 micron size and 20 micron size particle, the deposition rate also increases. But in these cases, we cannot get continuous coating on the CFRP. When we focus on the particle size effect, 5 micron size could cover the whole surface at 300 temperature degree, and the successful coating formation can be achieved. But larger 10 micron and 20 micron, we cannot cover all surfaces on CFRP. This is the actual cold spray process video. Let me play this video. So this is the actual process using a low pressure cold spray. So using the 5 micrometer particles, and we can get a continuous coating on CFRP. But why are smaller particles, in this case 5 micrometer particle, and gas temperature around 300 temperature suitable for deposition? We have to analysis for this point. First, we observed the surface SEM, surface image of each particle, and we can see the continuous coating when using the 5 micrometers. But at the case of 10 micron and 20 micron, the coating is not continuous, and now we can see resin part, the CFRP composed of resin and the carbon fiber, and the resin part is removed by the impact of 10 micron particle impact, yes. And the carbon fiber, naked carbon fiber, we can see. And so this figure shows a 10 micron particle in this operating condition could result in the erosion of CFRP. And a more larger case, 20 micron particle size, we can see this is a high magnification SEM, the carbon fiber fracture and also erosion, severe erosion occurs by the 20 micron particle impact. And interestingly, the small particle can deposit. We can see a smaller particle in this case, but particle selectively deposited on the resin. So resin bonding between resin and the particle is good, but bonding on carbon fiber is maybe impossible from this figure. So bonding, the adhesion on carbon, adhesion on resin, and also the bonding between the resin and the copper particle is really important to improve the adhesion strength or cover the surface. To investigate the particle momentum, we performed the CFD simulation by using commercial software ANSYS Fluent. We set the cold spray dimension, and we changed the inlet gas temperature from 260 to 300 and 340. And we estimated the particle temperature, velocity, and kinetic energy in front of substrate before impact. And the particle size also changes from 5, 10, 20. In this simulation, we use the constant particle size. So no particle size distribution. This is a result of temperature and velocity and also kinetic energy of particle before impact. First, we focus on the particle size effect. The particle temperature for each particle size, particle temperature increases for increasing gas temperature. And velocity and the kinetic energy, we focus on the kinetic energy. When the kinetic energy increases by an order, because yes, this is one order, and one order increases when the particle size is doubled. And also let me move on to gas temperature effect. The gas temperature effect, particle temperature increases with increase in gas temperature. But however, gas temperature effect on kinetic energy and velocity was negligible in this simulation. So So gas temperature effects should be thermal effects on particle and substrate. So we measure the substrate temperature by infrared photography. In this experiment, we just export the gas, hot gas at 300 temperature degree, no powder feeding, without further feeding. Just export the gas on the substrate and measure the surface temperature of CFRP. This condition is the same of cold spray condition. So like this, the nozzle sweep on the cold CFRP, and we measure the surface distribution of the CFRP. Now, this slide shows the 260 case from, 300 and 340. We can see the, now this slide shows that this temperature distribution in this white box, the temperature distribution around the nozzle outlet, we can see. Now, when we set the gas temperature to 160, maximum temperature is about 190. Actual materials cannot open in this presentation, but this substrate, the gas transfer temperature is around 150. So this figure shows the surface temperature around the nozzle outlet exceeds the gas transfer temperature, and the thermal softening effect occurs on the substrate. When increasing the gas temperature, also the maximum temperature and higher temperature region expanded, and 340 cases reach up to 250. But all cases is less than melting point. This material melting point is about 300 temperature degrees. So substrate surface temperature at the nozzle outlet, just below the outlet, is distributed between the gas transfer temperature and the melting point. This thermal effect is also should be effective on getting the coating on CFRP. So I draw the simple map on the coating window of CFRTP. When increasing the particle kinetic energy, in this presentation, it means particle size effect. The severe carbon fiber fracture and resin erosion occurs when increasing the particle kinetic energy. And we change the gas temperature, it means surface temperature change. Over the gas transfer point, we can get a continuous coating. So this SEM cross-sectional image is 5mm particle size and 300 gas temperature case. We can see no carbon fracture, no carbon fiber fracture occurs, and maybe mechanical interlocking is coating mechanism. So it's important to select a particle kinetic energy that does not cause erosion of CFRP, and the use of small particles smaller than 10 microns is an effective method. But smaller particle is sometimes easy to occur clogging. So in our case, 5 micron is under limit. We tried the 3 micrometer particle size also, but clogging occurs and we cannot realize stable powder feeding. So let me move on to development of cold spray coating for protecting CFRP from lightning strikes. We performed lightning strike test on cold spray coated CFRP. The lightning test facility is Ottawa Electric Company in Kobe. The test method is arc entry test, and the current waveform, we adapt the component A. The peak current value is 40 kiloampere or 70 kiloampere, and test specimen size was 100 millimeters square. Before we see the cold spray result, first I will show you the CFRP, original CFRP samples result. This is no protection, no lightning protection sample. Yes, so we can see severe damage of CFRTP, the carbon fiber fracture occurs, and also we can see the fires on CFRP. The next is CFRP with conventional metal mesh. So with lightning protection system. Yes, this result looks good because no carbon fiber fracture not occurs, and also the no fire we cannot see. We can see no fire. So this is a surface picture before and after lightning strike test with the conventional metal mesh. This is a metal mesh before the lightning strike test, and after the test, we can see mesh is dispersed from after the lightning strike test, but visually we cannot see severe damage on CFRTP. So this metal mesh protects against the severe damage to CFRTP caused by lightning strikes. So we performed the same experiment on copper coated CFRTP, and this test was 40 kiloampere, but we used 70 kiloampere to cold spray samples. Upper figures is before the lightning test, and after the lightning test is below figure. Now we tried the full surface coating, and also grid pattern coating, similar to mesh pattern, so metal mesh. And we can see after the test, maybe this full surface coating, we cannot see damage on CFRTP, and also grid pattern coating, the damaged area looks wider than full surface coating, but this metal mesh, I can say this metal mesh reduced the damage on the CFRTP. So this metal mesh and also full surface coating act as a lightning protection coating, reducing damage to the CFRTP. This is a street metal plate we used for making this grid pattern coating. And we performed the X-ray CT analysis of CFRTP to estimate damage inside the CFRTP. This result is original CFRTP result without lightning protection. So we can see this side is a lightning strike plane, and we can see the crack propagates in parallel to surface, so the carbon fiber direction. So this is XZ plane, also YZ plane, and this darker color area is a damaged area. So we have to, some lightning protection system is necessary for CFRTP. And this is a result sample with metal mesh. The metal mesh case is we cannot see damages inside samples, and no crack occurs, and also no delamination occurs, and very great technique I thought in that experiment. The metal mesh is caused no damage. And this is a result of the cold spray samples with full surface coating. In this case also, we cannot see damage inside CFRP, and also, maybe darker color we cannot see, and also crack and delamination we cannot see in this picture. So no crack were observed inside CFRTP. This full surface coating can differently reduce the damage to CFRTP. At last, this is a metal mesh case, a grid pattern coated case. We can see the crack occurs in this case, and the metal mesh can reduce the damage to CFRP, but little crack was observed in the sample. So improving maybe this is because low electrical conductivity of CFRTP grid pattern coating. So we have to improve the electrical conductivity of grid type. So each coating line coatings density, and improve the electrical conductivity of each line. And also we have to consider the grid spacing and grid width or something, some parameters. So let me summarize lightning protection performance of cold spray coatings. When considering the cold spray coatings on CFRTP, most important point is the coating electrical conductivity. So we should use highly conductive materials such as copper, and also coating density is really important. This is not a pure copper coating. We mix some polymer coating with copper and high resistance coating. We cannot protect the CFRP from lightning. And grid interval is also important. When using a rough grid patterns, we cannot protect the CFRTP also. So because, yes, so for electrical conductivity, this conductivity is a very strong relation with the Joule heating So improving conductivity is very important. Also for grid pattern case, we have to design to improve the arc dispersion phenomena. So the lower density on CFRP, the system to expand the arc route and reducing density, current density is really important. So let me summarize my presentation. The objective of this study was to develop a lightning protection technique of CFRTP using low pressure cold spray method as an alternative to conventional metal mesh lamination. For cold spray metal coating on CFRTP, it's important to select a particle kinetic energy that does not cause erosion of the substrate. And use of particle size, particles smaller than 10 micron is an effective method. And also, cold spray copper coating acts as a lightning protection coating, reducing damage to the CFRTP substrate. Densification of the coating is required to improve the coating property for lightning strike. This presentation is based on the result obtained from the project, the NEDO. So thank you for listening.